again, no one is saying this is going to come tomorrow. It really looks like it's probably on the order of 20 years. Okay, we need that kind of engineering commitment to it. But at the same time, there's no magic, no miracles that have to occur.
Yeah.
And it's just, if you make the investment, we can have this come.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a fantastic week and have a brilliant weekend in store. Today, we're going to be discussing the future of particle physics experiments and the intriguing possibility of building a Muon collider. The Large Hadron Collider has fundamentally altered the high-energy particle physics landscape over the past 10 years. The discovery of the Higgs boson in 2012 was a monumental triumph. It validated the prevailing hypothesis for the origin of mass of fundamental particles and illuminated a clear path of study extending into the future. Exquisite precision studies of the Higgs boson and its interactions are now essential and represent a potential portal to answering some of the most fundamental questions about the nature of our universe. However, for many experimentalists and theorists, the success of the LHC has been bittersweet. The lack of clear signals of physics beyond the standard model at the TeV energy scale has been disappointing. We found no supersymmetric particles. We found no extra dimensions. We found no dark matter. For some, particle physics is reaching a crisis point, and the doomsayers of particle physics are circling. Where do we go from here? The LHC has provided a clear picture of the high-energy frontier from data that we did not have a decade ago. There is a Higgs boson at a mass of 125 GeV, but there is then a potentially huge energy gap to any new physics phenomena. It's clear that we need to study the Higgs boson with precision and unlock its mysteries, but we now also need particle physics experiments that leap as far as possible into the energy void and reach collision energies many times higher than those at the LHC. Experiments that shine a light as far into the distance as possible and illuminate the nature of new physics. Put simply, we need both precision and energy reach. Some scientists believe that the best way to reach higher energies and undertake precision physics may be to build a new type of collider, a Muon collider. Such a collider would be the first particle physics experiment to collide unstable, short-lived particles, muons, a heavier cousin of the electron. To help me dig into this fascinating idea and understand why a Muon collider might be the next and most sensible step for the particle physics community, I'm joined by a fantastic special guest, Professor Patrick Meade. Professor Meade is a professor of physics at the C.N. Yang Institute for Theoretical Physics at Stony Brook University. He completed his PhD in high energy theoretical physics at Cornell University before continuing to postdoctoral positions at Harvard University and the Institute for Advanced Study. His research interests are mostly focused on physics beyond the standard model, including baryogenesis, collider physics, dark matter, flavor physics, supersymmetry, thermal QFTs, and QCD resummation. He is also interested in current and future experiments that may elucidate the properties of the universe, including the possibilities for future lepton colliders, and maybe a Muon collider. To that end, Professor Meade was the lead author of the Muon collider contribution to the US SNOMAS process. So who better to help me dig into this fascinating topic? So, Patrick, the obvious first question is, what are muons and why would a Muon collider specifically be the sensible next step for particle physics? So, you got your soapbox. Here we go. Why are we going with a Muon collider?
Well, I'm going to kind of preface everything from my perspective as a theoretical physicist, not an experimental physicist or accelerator physicist. So from my perspective, we know there's kind of many different length scales in the universe. And we're all familiar with telescopes going to bigger and bigger distances, trying to see things. Everybody's excited by JWST.
Yeah.
On the other end, we've always kind of found new things as we go to smaller and smaller distances. And that's what particle physics is really about. And we know that there is a theoretically smallest distance we can get to, the so-called Planck length. And that turns out to be a Planck energy, Planck scale in terms of where we can go to with colliders to see these smallest length scales. So as a theoretical physicist with no kind of skin in the game on a machine, so to speak,
Yeah.
I'm just interested in what can get us to the highest energies.
Yeah.
And then it's a matter of how do we get to those energies? And we've had for the last 60 years or so different ways to get there using particles we know about, like the electron and the proton. Probably everybody's familiar with them at some level.
Yeah.
But the point is, we've gotten to this sort of region in human evolution where the machines that we build are gigantic, right? The LHC, you always hear the statement that it's the biggest machine ever made by humans.
Yeah.
And if we want to go to higher energies, we really need to develop some sort of new technology. Yeah. And the idea there is if we use particles that are not everywhere around us, these kind of new crazy particles, the muons, we're able to kind of make a technological leap and get to these highest energies.
Yeah. So these muons are heavier than the electrons, which allows us to accelerate them around corners, accelerate them around these accelerators to much higher energies because they don't lose as much of this synchrotron radiation. Is that kind of where we're going with that?
Exactly. So there's always kind of been two main ideas where you could either make protons, which are pretty heavy particles, they can go in rings and get to super high energies, or you can use electrons, and then, as you said, they lose energy when they go around corners, so you can't get them to very high energies. Or you can kind of go in a straight line with them, but even there, technologically, you can only get to kind of what they call the so-called 3 TeV scale or so 3 trillion electron volts. And we really want to go higher than that because the LHC is already at 14 TeV. Yeah. How do we get higher than that? Well, you can use muons, which are fundamental particles, which can really pack all of their energy in a punch, rather than protons, which are kind of like big bags of other particles that you can't use all their energy.
I always think of it as like throwing 2 bags of potatoes at each other, right? You're not going to get that full energy of the 2 potatoes smacking into each other, which is kind of like dealing with a proton. You talked about getting to the highest energy. So I guess from a theoretician's perspective, we've now reached a kind of uneasy situation, haven't we, where we know the Higgs boson is there at 125 GeV, but we didn't find necessarily as much of the new exotic stuff as we would have liked. So talking about things like, supersymmetry or dark matter or extra dimensions or any of the other things we were hoping we might have found at the LHC. So I guess there's sort of, or at least what I see, and you can speak to this, is a kind of bit of uneasiness in the field where we both want to look at the Higgs in detail and with precision. So that calls for lepton colliders, usually have been electrons, maybe muons in this case. But we also need to do this leap in energy to kind of assuage people that, look, we understand maybe we didn't find as much as we hoped we would, and we need to leap as far forward as possible to try and open up some doors, because there's a lot of people who are, on the more contrarian side, maybe who are saying the field is sort of stuck or, kind of grinding to a halt. What do you make of that kind of idea?
Yeah, I mean, I think what we're seeing from the LHC is roughly what you said. The fact that we found this major new aspect of the universe, the Higgs, and then we haven't seen anything. So we need to be doing the preparation to make a kind of a jump in energy to keep looking forwards. I mean, from the perspective of being completely agnostic and saying, like, I want my biggest telescope or my best microscope, I'd like to go as high in energy as possible. Sure. But at the same time, I think there's another argument independent upon, like, whether you care about supersymmetry, extra dimensions, kind of all these fancy buzzwords. What we found with the Higgs, it's the single particle responsible for everything we see in the universe, essentially. And the funny thing is, everything about life that we know it depends upon a minus sign, right? somebody wrote down a potential with a minus sign that allows all of life to go forwards. And it's similar to kind of back in the day for condensed matter systems, where they had a Landau-Ginzburg theory for spontaneous symmetry breaking, but that didn't explain the actual theory behind superconductors. There was a microscopic theory which explained why we have this effect of spontaneous symmetry breaking. So I'd say, independent of all the hopes of theoreticians, it's just we're confronted with the fact that the Higgs is the weirdest thing we've ever seen. It's one minus sign someone wrote down that's supposed to explain the entire universe. And it would be really nice to understand what is the origin of this universe that we see around us. So getting to higher energies to kind of figure out whether there is something like Cooper pairs that explains the origin of this. We really just have to go forward. So, I mean, I don't think you have to buy the theorist's best ideas, but it's really kind of an imperative to say, if we care about why we're all here, we have to do this type of physics at high energy.
So we're searching, and at the same time, because muons are point particles, we could still do these precision studies of, for example, the Higgs and looking at all of its details. So it's kind of a nice combination of the two. I guess one of the questions that people will raise is that there are a couple of ways we could go about this. The kind of received wisdom at the moment, or the current trajectory, seems to be that we're going to build this 100-kilometer long E plus E minus collider near Geneva to succeed the LHC, and we will therefore do our precision studies of the Higgs, because electrons are leptons and they are point particles. We can do these precision studies, and this will be the future circular collider, which again dwarfs the LHC. You were talking about going to big machines. This one is going to be 4 times as long. Why might a muon collider, do you think, be the better way to go than what seems to be the received wisdom at the moment with this future circular collider?
Well, I certainly think E plus E minus colliders are kind of an interesting first step in terms of studying Higgs precision.
Yeah.
The problem is, if you really want to ask these questions about where we all came from and the origin of matter and things like that, it turns out that you don't just need to study the Higgs at low energy. You also have to study it at high energy too. So we have this potential, like I said, this one weird minus sign, but these E plus E minus colliders that are circular can't actually access anything about this Higgs potential in detail, and you have to go to these high energies.
So there's higher order terms that we want to look at as well in that potential, right? Okay.
Well, it's just kind of producing two Higgses. The circular collider, the FCC, it's designed to look for a production of a Z boson and a Higgs boson at the same time, and you kind of sit there and watch that. But what we really want to understand this potential, is we want to produce 2 Higgses at a time, or 3 Higgses at a time. Yeah. And you need energy to do that. And unfortunately, the future circular collider for E plus E minus can't do it.
Yeah.
You need to go to a linear collider or HH. And so the muon collider allows you to make that jump where you get both precision and you can access these new processes.
And I guess, is it fair to say that, and I guess you kind of alluded to it earlier, that there's a limit that we can go with these, right? We talked about a 27-kilometer long LHC. We're now talking about a 100-kilometer long future circular collider. We're running out of room, aren't we? If it's not now, it's probably going to have to be next time, because what are we doing after that? 500 kilometers, thousands of kilometers. We're running into space constraints. It's going to be geopolitical constraints, because we're going through some countries that might not want to have this thing going through or under their land. So at some point we have to make this transition in technology, right?
Exactly. I mean, there have been even crazier ideas. Like Fermi long ago had this idea of a globotron, where it was a collider that went around the entire circumference of the Earth in outer space.
I've seen the moon one. I've seen the moon one. Yeah.
Yeah, the moon one as well. Yeah. But once we kind of go back onto the real axis of what's potentially doable, it really is a matter of, we're going to have to start making technological changes and advances. And the nice thing is, in the timescales we're talking about, the Muon collider seems to be the thing that's most ready to go forwards and let us make this change rather than just building a 100-kilometer tunnel.
Mm. And I guess are there any other benefits to building this Muon collider? So I was looking through some of the notes, and you talked about energy reach, which is obviously a huge thing. What's the expected footprint on the Muon collider for an energy that's similar to the future circular collider?
So, I mean, roughly the scaling, you can imagine sort of a 10 kilometers sort of collider ring. So it's kind of LHC scale within order one or a little bit smaller.
Okay.
It turns out that these colliders are a little bit different in terms of how they're structured, and the collider ring is actually the smallest part of.
Yeah, we're gonna come on to that because that is a little bit weird, but we'll explain why that's the case.
Yeah, but yeah. So roughly the case is, if you wanted to use a Muon collider, you could build it on the scale of the LHC at CERN, or if you did this in the US, there's plans to fit it inside the Fermilab site, which is much smaller than what the LHC site is currently.
I think I've got a nice picture of that somewhere, so it can fit. It can fit nicely
Just
inside.
barely, yeah.
Just
They want
right
the-
on the edge here. Yeah, somebody's house gets sort of clipped at the edge, but more or less we're there, so we can fit it in there.
Interesting geopolitical differences where in the US, apparently everyone owns the land underneath, whereas in Switzerland, you don't technically own the land all the way down to the center here.
So I have to be careful about whoever owns the farms on top. One other thing I saw was the energy efficiency of it. It seems to be far more energy efficient than linear colliders at similar or lower energies. Why is that the case?
Exactly, because effectively what's happening, because the muon is unfortunately a particle that decays in about a microsecond or so, and as you give it more and more energy, it lives a longer and longer time. So if you go to high energies, that's where kind of the muon collider sings, because you have more and more of these muons that you can really push together and collide. Whereas linear colliders kind of have this flat shape that if you want to kind of go to higher energies, you just kind of need to put more and more power into it. So yeah, this flat curve that you're showing here, whereas the Muon collider has this nice feature because it doesn't have to worry about synchrotron or Beamstrahlung or any of these things that E plus E minus does, and you're circular, it just becomes more and more power efficient at higher energies, which is a real concern as well. Not only the geopolitical aspects of, do you want to build under this person's land or this country's land, but when we talk about power consumption of colliders, I mean, you're talking about the land of 100 megawatts to higher. And if you're kind of closer to that, you're fine. But if you try to imagine a collider that took like 4 terawatts, you're not going to get permission or have enough money to pay for the power bill.
Yeah, it doesn't sound good either in the in the world of concerns of climate change. So I guess another good thing with the circular design as well, because people obviously go to linear designs, they start to talk about things like plasma, wave field acceleration to try and get these things more compact. But what's the problem with using these linear colliders? I guess it's very hard to get the luminosity right, because you're not circulating these muons past one another over and over again, so they're kind of a one-shot deal. Is that really the downfall of linear colliders, and why we're not moving to linear colliders to get over these synchrotron losses and move to high energy? Just a luminosity concern?
Yeah, I mean, there's really kind of two issues for the linear colliders where, it's only kind of you smash once and then you're done, because you don't get the circular part for the luminosity. The other problem is, even though it's linear and you don't have this synchrotron radiation loss, once you kind of get to higher and higher energies, your power bill gets bigger and bigger in terms of the power consumption for the linear colliders. And then at the top of it, you're really kind of limited by that, and you have to bend the beams eventually to interact. I mean, you can't be shooting them exactly at each other. They kind of have to be off center and then come to an interaction point. So there's also so-called Beamstrahlung effects, where just kind of moving that beam can create lots of photons that you lose energy. So linear colliders are a great solution, but with current technology like CLIC, which is kind of the bleeding edge, you're really kind of stuck at the 3 TeV scale, maybe 4 TeV. And we're really interested in going parametrically beyond that because of all the LHC data that we have.
Yeah.
Plasma wake field potentially can go well beyond this kind of like 3 TeV barrier that we have now.
But it's probably far off
Problem is,
into the future, right?
yeah, I mean, it's always an optimization thing. Like you could say, like, let's wait till we make some miracle technology, and in 2100 we'll build the next collider. But
Yeah.
this is kind of a pursuit that we're on, and I think the Muon collider is the one that's kind of the closest to on shell.
Yeah. Yeah.
And lets us make this jump in energy.
Yeah, it's like let's wait for fusion and then we'll fix climate change. We need to do something. We need to do something now, right? Which is optimized for the current technology. So that makes sense as to why we would be interested in this collider, and maybe why it's a competitor to something like the Future Circular Collider, which seems to be the thing that is most getting pushed most at the moment. The next question I had is, why have we not done this before then? You talked about the benefits of this. Why is it only now that we're seeing people kind of come out and be more vocal about this, or push for a technical design report for the Muon Collider? Why is the time now for a Muon Collider and it wasn't 10 years ago, 15 years ago? Is it just that the technology is now catching up to that dream of a Muon Collider?
Yeah, I think it really, because the idea of a Muon collider goes back probably more than 50 years to some Russian scientists, and then some people in the US thought of this as well. And at that time, I mean, the problem is, compared to electrons and protons, which are just living there, sitting around forever, the muon decays in order of microsecond. Yeah. So it's kind of, it's a technologically huge challenge to figure out, how do you take something that lives only order a microsecond, yeah, and then make it go around an order 10-kilometer ring and do all these things? So the ideas were there, but only kind of recently, in the last decade or so, has technology advanced to a point where this is not some futuristic miracle. It's just a hard engineering problem. Yeah. And I think it's also been a factor of, we had plans all the way through the LHC in terms of how to kind of get to the energy scale we're testing now. And like you said at the beginning, like what the LHC has seen says we need to go to these higher energies. And there wasn't as much imperative before about how do we get there. It used to be that, hey, we build the LHC, then we'd build an E plus E minus at like 250 GeV, and then we'd kind of be done. We'd just be like figuring out the spectroscopy, all the new particles we found. It's really kind of, the LHC has shown us the way that we need to start thinking about how to get to these high energies.
Yeah. So the first problem here, just to kind of crystallize it out for people, is that at rest, these muon particles that we have them in the environment, we have them streaming down from space, but to create a kind of collimated beam, we have to create these things from scratch. We have to get them up to energy. We have to collide them, and if they're at rest, they decay in 2 millionths of a second. So we need to create them, we need to focus them into bunches, we need to accelerate them, and we need to smash them together before they decay. And I guess just to make it a little bit easier for people, what is the time window that we have to go from creating these to smashing them together? Because we can gain some time back by accelerating them quickly, right? And we get the relativistic time dilation of their lifetimes.
Yeah, so this is the cool thing about a Muon collider is you're using this idea of relativity to kind of offset quantum mechanics. Okay. So quantum mechanics in this picture you have up there says, well, this particle can actually decay to lighter particles in a very quick time, but then you can use kind of the energy that you put onto this to make it live longer and longer and longer. Now, it still has the probability to decay at any time, but you can kind of give the survival chances better and better and better as you kind of make this thing more and more energetic.
Shift that mean lifetime up to longer values.
Exactly. And I mean, the reason why this collider is so new is because you have the same issue of, like, if you take electrons or protons for any collider, you have to kind of bunch them all together, make a beam that's kind of focused enough so that when you smash it together, you have a chance of some of these actually hitting each other. The thing is, the technology for kind of doing this cooling of a beam that you use for electrons and protons, like, it takes normally on the order of an hour that you can kind of spend the time to cool the beam. if you're sitting at rest with order a microsecond, a millionth of a second, an hour is a really long time to hope that you have any muons left over. So that's why it requires this new technology to kind of get them to stick around and cool faster.
So that's the first problem. The first problem is that these things decay. They want to disappear. They don't want to be hanging around. And I guess a kind of corollary of that is you have all of this stuff which is spraying your detector, right? So as you're circulating these muons around any sort of machine, they're falling apart into these electrons, and these are spraying parts of your detector, which I get. Spraying just everything in your machine, essentially. So I guess everything needs to be either shielded, or if you have anything that's superconducting, for example, needs to be high temperature superconductors. So I guess it raises more engineering concerns than you would have with an E plus E minus collider.
Yeah, it turns out that luckily we don't have to go to high temperature superconductors. There's different, like you said, everything's getting sprayed. So like you can talk about different parts of the machine. Yeah. But for example, just in the collider ring, when these things are circulating around and have to be bent by magnets to stay in this circle, the idea is essentially you have kind of an order a centimeter tungsten shield around the beam pipe. And that's apparently sufficient to kind of dampen all the effects of these electrons flying out that would give you quenches to the magnets.
Tungsten's expensive, you can also imagine, though, isn't it?
I mean, it turns out the estimates that the Muon collider actually turns out to be one of the cheapest options as well. Because you have to keep in mind that, yes, the actual components, you might have more components compared to a normal one, but you're also smaller. Yeah. So you don't have to make 100 kilometers of this. You only need to make order 10 kilometers of this. Yeah. So at least what was estimated from this snow mass process is kind of, not only is a Muon collider really cool in terms of the physics, but it's also one of the cheaper options out there, especially if you want to go the high energies.
And that's always good when you're trying to sell it to a funding body, right? It's not only is it better, but dollar bills as well is always a good thing to be going along with. So those are the two big problems with the Muon collider. This would be the first time we've smashed together short-lived unstable particles. So usually we're dealing with electrons, positrons, protons. These things are stable, they hang around. These things decay. And also they spray our machine with radiation, which we have to deal with. So if we just go on to quickly kind of go through the steps, how would this machine look and how would it function? What are the general steps? And then maybe we'll very quickly go into the specifics of each step. What are the basic building blocks of a Muon collider and how would it look?
So, of course, this is all going to be with a theorist perspective. So, I put
a slide up to help you, just, if there's problems.
Yeah. But basically, the first problem is, how do you get these muons? Yeah. Right? These particles aren't naturally living around us. We do see them in cosmic rays, but that's because they have super high energies. Yeah. So the basic idea is we first have to somehow make the muons, and that was the first part of your picture, where we have essentially protons coming in, smashing against something, and we exploit kind of a resonance in this to kind of get the most out of this, where it's kind of a delta resonance that then decays to pions, and then like the last part of this you see is that the pions then decay to muons.
So it's like a tertiary beam. The third thing along the chain is the thing that we actually want. So we smash into some sort of target. It's really hard to get these out. Yeah, we create the pions, then we let the pions decay, and then we're like, okay, we want these ones. These ones we keep.
Yeah. So luckily, this part isn't new. Yeah. We actually do this all the time right now in modern particle physics because there's a whole sector of high energy physics called neutrino physics, where they need to get lots and lots of neutrinos. Yeah. And the best way to get neutrinos in terms of this is that the muon after this kind of
there's another step on the right hand side with you can go another one.
Yeah. The muon eventually decays and gives you a whole bunch of neutrinos. So this part, we already use this at any of these kind of neutrino beam experiments currently. So this isn't new. The only thing is we need to make sure that we kind of have an intense enough beam of these muons, which is kind of a little bit beyond what we're currently projecting with the so-called LBNF Dune project that's going to be at Fermilab. But that's the basic idea. We need to make these short-lived particles somehow, and the best way we know right now is to smash protons on a target.
So you need a very, very intense proton beam. Luckily, we know how to do that. We've got the PIP2 Linux at Fermilab. We've got the L8T, which is smashing protons together. There's no problem with creating very intense proton beams. We might have to do a little bit of work on targets so that we can, have targets that can withstand these extremely high power proton beams. But it's certainly not outside of the realms of possibility, and it's not anything that's kind of quantum leaps ahead of where we are at the moment. You talked about cooling. So once you've created these muons, do you want to briefly explain what you mean by cooling? Because it's not good enough, is it, just to create this kind of haze of muons if you then want to put them forward to be beams for a muon collider?
Basically, when you create these muons, because it's kind of this multiple step quantum decay process that gets there, they're not all flying in the same direction, right? Once these pions eventually decay, you'll kind of get order 100 MeV, 100 million electron volts of momentum of these muons, but they also might have like 30 or 40 MeV in another direction. So if you want a beam that eventually collides together, you're going to have to somehow shrink this phase space of where all the muons are coming down. To kind of give people a rough sense of this is like after the original creation of this, these are spraying out everywhere. So you have to first kind of collect them in kind of a big group.
Yeah.
And you do that with a kind of a gigantic capture solenoid.
Yeah.
And then at the beginning of it, you kind of got a ball of muons that's of order the size of a basketball. But a basketball is still way too big, because if you throw two basketballs of muons together, they're never going to touch each other, okay? They're just going to pass right through each other. In the end of the day, we're trying to get this down to the size of beam pipes, and with phase-space distributions that these things will hit each other. So you kind of need to get this thing down to kind of order millimeter size. Yeah. So to go from a basketball size down to a millimeter size, and the fact that all these particles have different momentums, you need to do the so-called cooling. And the reason why it's called cooling is because if you think about from the frame of the muons traveling along, then all these particles, all these muons are kind of distributed in different directions. So that's why you can think of the beam having a temperature. Yeah. And now when we want to shrink this beam down, that's why we call it cooling. And as I said, unfortunately, all the cooling that we do with normal beams just takes too long. So you come to this new idea, this cooling.
So we're back to the idea that we've got to do things quickly. This is the new thing. This has to be done quickly. Usually we could have different solenoids. We could take time. We could send them through different magnetic and electric fields, and that would all be fine because they just sit there forever. Muon's not the case. We need to cool these things damn quickly, get them down to this millimeter size beam, as you said, as quickly as we can.
And the basic idea for doing this is this process isn't new. I mean, it turns out to be something called the beta block formula. So this is something obviously many, many, many decades previously found. But if you pass a particle through material, okay, this material is made up of a bunch of atoms. And what happens is that, of course, my muons that are passing through this material can knock into either the electrons or the protons that are in this material. And if they knock into the electrons, because the electrons are so light, essentially they just ionize the atom. The electron gets knocked out. That's why this is called ionization cooling. And the muon then loses some energy in this process. But the idea is we're going to lose the energy. We're going to lose in kind of the transverse directions as we're going down here. But if we can kind of, after we lose the energy and make our basketballs smaller, if we just did that, the muons would still decay. But then we kind of have to give them a boost of energy to kind of get that special relativity time dilation factor back. And the idea is by doing this over and over and over again through a cooling channel of cooling, accelerating, you can start with this basketball and then come up with a beam that's just as good of a beam as electron beams or proton beams that eventually then you can smash together.
So just to show people kind of what's happening in this diagram, As Patrick said, you pass the muons through these absorbers, and these absorbers are through various materials. They knock the electrons out, and the beams lose energy in all directions. But then you pass them through an accelerator coil, which accelerates them only in the forward direction. So you're losing this transverse momentum, but then putting back the forward momentum. So everything is kind of cooling, and the vectors are moving towards being only in the forward direction. So you've only got momentum in the forward direction and cooling in those sideways directions. And this is a very quick way of doing the cooling. We can't do this in traditional ways. And I believe one level of this has been demonstrated here in the UK at mice, but they haven't actually chained all these things together, right? We haven't got a demonstration of absorber, accelerator, absorber, accelerator, absorber, accelerator. We've got one chain of where this actually worked, but there's probably a bit of R&D work that needs to be done on this cooling. Is that fair?
Yeah, that's a perfectly fair statement. On paper, there's a cooling channel design, this so-called map design that you had on the previous slide.
Yeah.
And we know, I mean, in terms of full simulation, this has kind of gone through. But in terms of actually building anything, so the mice collaboration did this in the UK and has demonstrated this kind of transverse cooling of the beam. But then we need to accelerate this, cool it again, accelerate this, cool it again, accelerate this, cool it again. And it's, in principle, doable. It's just you want to make sure the engineering works, because an example of why this is a hard engineering problem, I mean, as physicists we can say, hey, you just do this and like everything works on paper. But for example, because you have to kind of after each step focus the beam with magnets to kind of aim through this absorber well, then accelerate it and then focus push through the absorber, you're using kind of superconducting magnets.
Yeah.
But then the things that you accelerate it with are copper RF cavities,
Yeah.
which are nice and warm with many megawatts of energy in them. So
you've got huge electric fields in these cavities, which have to be run inside massive magnetic fields of a solenoid that's wrapped around it. And the interaction between those two could make it a hard engineering problem, even if both of the two individually look like they should work in a vacuum.
Because another accelerator is like you have all the time in the world and you can separate these components.
Yeah.
And now we're telling them, put everything right together, the cold things and the hot things, and make sure it works. Now, in simulation, all works, but I mean, this is why there needs to be investment in the engineering R&D for this, because it is a hard problem. I mean, it's not like we're going to build a Muon collider tomorrow, but at least the actual physics behind this idea of ionization, this is order a century old now. Yeah. I mean, this isn't like somebody just came up with this yesterday. So it's doable, but it's something we need to demonstrate.
And there's some really interesting advancements that were shown in this nice talk. Some of the slides you're seeing are by Daniel Schulte and Mark Palmer, so they should get a mention because I'm basically shamelessly stealing some of their slides to help people understand what's going on.
Yeah, they're the Daniel's kind of spearheading the European effort, the International Muon Collider Collaboration, and Mark Palmer was the head of the MAP program in the US. So these are two luminaries in this field.
Exactly. So there's some really interesting advancements in this. Like you say, you're going to have to operate these cavities. We've got cavities that can do 50 megavolts within 5 Tesla fields at mu cool. We've got these solenoids which have been able to go up to 32 Teslas with high temperature superconductors. So there's advancements been made in this field, and like you say, it looks like all the pieces are there, but you have to put in some work to make sure you can slot all these things together, right? Because until you do that, you can't see where some of the gremlins might be in the interactions between these things. So exactly, so that's a key step going forward. So we create these muons by smashing things into a target. We focus them into a nice beam. Then we're off to the races, accelerating them. Now, what's the problem with doing this? I guess you have to do it super quickly again, right?
Yeah, I mean, it turns out that the acceleration part is relatively straightforward. I mean, in the sense that
it's relatively normal compared to other experiments, right?
I mean, people shouldn't think of like muons as having all the crazy steps, because a muon at its heart really is just a heavy electron.
Yeah.
The only difference is it's heavier and it decays.
Yeah.
So if you can somehow kind of collect the beam, collect all these, make them collect them and make it into a beam, the acceleration's kind of the acceleration that we do with protons and electrons. Just like you said, you just have to do it quick enough so that you don't have all the muons decay on you. So like you'd eventually get to your detector and nothing lights up because they all disappeared on you. So that you don't want that to happen.
Yeah.
But in terms of the actual acceleration process, the technologies are all kind of straightforward. The only difference is instead of kind of like bringing them all together kind of slowly up to speed, you want to do this quick enough and kind of not in like a million different rings spanning a whole complex everywhere.
Yeah.
So the idea is you want to be able to, for instance, have magnets that can ramp up fast enough. So that's kind of the one piece of technology that's a little bit different or a little bit pushing the envelope compared to what you do with the LHC or what you would do at a future circular collider.
So when we think of the LHC, just so people are aware, I'm sure most people will be aware. You have these rings which are essentially, it's beautiful because they're basically just past experiments at lower energy, which circulate these protons over a small range of energy. Then you go into a larger ring, you accelerate over another range of energy. Eventually you go into the LHC, which accelerates up to the full energy. That wouldn't be the case with a muon collider. You would have to do all of that acceleration very, very, very quickly. The LHC might do it in of order an hour, like you said. In here, we're going to need to do it in order of, I guess, seconds, right? So we have one ring.
So the idea is just kind of minimizing the length these things travel in any way, shape, or form, so you have as many of them left over to use for your experiment. And I mean, there is a full kind of design at this all the way out. These fast ramping magnets, to kind of be able to do this, they're kind of within sort of an order one factor of kind of current ramp rates for magnets now. So again, there's another piece of the technology that we have to still go beyond exactly where we are now.
It's close, but we can see it on the horizon to get there.
Yeah, exactly. So the nice thing is, it's not just for muon colliders. I mean, all these kind of bits of technology have applications elsewhere, like making magnets that have like very strong fields. Like they're magnet experts, like at the National High Field Magnet Laboratory and at CERN and at Fermilab, that this is just the people's job. They want to have the best fields they can get to. And so all these pieces of technology, luckily, are being developed in other parts of the world and for other purposes. And like you said, it's really a matter that we just have to take all these things and do the studies of how can we put them all together and make sure the engineering really locks up all these components together.
And like you said, we accelerate up to high energy, which is relatively conventional compared to something like the LHC. And then the final thing is smashing these things together. And we kind of raised this point earlier, but in somewhere like the LHC is the largest ring, and that's where the collisions happen. In this case, you go from a larger acceleration ring into a smaller collider ring. So could you tell us why that is and why that's important for the operation of the muon collider? Because it's a little bit counterintuitive when you see it the first time.
Yeah, it all just again comes down to the same thing, that the muon decays. So we need to make it live we need to have it go the shortest distance possible. So for the LHC, what essentially kind of sets the size of these rings, of course, also is the strength of the magnets, that you can kind of bend them to keep them in a circle. But here, the collider ring's the part where the muons will kind of go around many, many times, kind of circulating around. And ideally, you want that ring to be as small as humanly possible, so that you can actually have some muons left over for your experiment. So that's why, unlike the LHC, where we can be leisurely, the protons will just keep spinning until we collide them all together, or we dump it because there's not enough of it anymore. Here we want to make the collider ring, where they're actually doing many, many passes, the thing that's as small as possible. And in principle, you could make it even smaller, and that would be even better for getting more muons. But then you just run in kind of this technological boundary of what are the magnets you can do versus how small you can make it.
So the deal here is that you have this acceleration pipe, but because you can't ramp the superconducting magnets fast enough, you have to make it a little bit larger. You have to deal with some normal conducting magnets. It has to be a little bit larger. But once you've got it up to its highest energies and it goes all in at one energy, you don't have to ramp. You can use superconducting magnets for everything, and you want to be as small as possible, as Patrick said, because you want as many passes of those muons as possible to give you a chance to have any collisions whatsoever left over at the end. So that's why it looks a little bit counterintuitive, but that's what happened. The last thing, Patrick, of course, in this is once you've smashed these things together, you actually need to see what's inside, so we can see if our theories are correct. We can see that we're on the right track. What's the difficulty with doing physics at a muon collider? Because it's all well and good saying we can get these things into beams, we can smash them together, if what we produce is no good for looking for physics. So what are the big problems with doing physics analysis at a muon collider, and how have those been looked into and potentially mitigated?
So naively, it should be great compared to the LHC because you're technically smashing together fundamental particles. I mean, that's why everyone loves electrons and they've been the source of precision machines.
Yeah.
But as you said, they're always decaying, and you get this so-called spray of particles that we name the beam and beam background, because not only do you have the muons, but you have the electrons that are coming along from all the muon decays. So you have multiple sources of particles that then can spray out into your detector. And so it's not nearly as bad as a proton-proton, where you're kind of smashing these bags of potatoes, as you said, and then fragments of mashed potatoes goes everywhere.
You can have that one, by the way. That one's for free. You can keep that one, please.
There you go. And then, but here we have these extra particles that you see coming into the detector. So you'd like to remove the particles that aren't the muons that you want to smash together. So the idea is, with this yellow on the picture here, is to make nozzles of tungsten, which hopefully are going to absorb a lot of the particles that come into this, so they won't make it in the detector.
So these muons are going around. Sorry, Patrick. These muons are going around. They're decaying to all sorts of, to electrons. They're interacting with the machine, and then they're kind of rattling into your detector, and you don't want that to happen. So you have these yellow nozzles here, which stop a lot of these particles getting into your detector window.
Exactly. So that's the kind of zero, kind of caveman sort of way to stop things. I'm going to just put a big shield.
Put stuff in front, and that, yeah, good.
Exactly. But of course, as you see on this picture, like, particles don't just have to hit this big tungsten shield. What happens is they can like hit other parts of the detector, and then a particle could bounce in, etc. And you want to not be fooled by these crazy things saying, hey, I found some new physics and give me a Nobel Prize. So the other idea is, since what you're interested in are the particles that hit in the center of your detector and make new things coming out, all these other particles are not coming from this.
So they don't trace back to that original interaction vertex.
Exactly.
Right.
So you can kind of go two different ways to mitigate this. One is understanding the tracking. Can you follow the particles back to that original part? But some particles don't leave kind of trails in your detector. You can have neutral particles that kind of just show up and light up a little bit of it. So tracking can help you, the shield can help you, but then the last part that's really the thing that has advanced in the last decade is the idea to use timing. Because if we have a bit of energy that shows up in one part of a detector, right, and we know when the collision happened,
okay.
We know.
So if you know when that bunch crossing happened between the two muons, you can have a sort of time gated window of when you expect to see things from that collision.
Exactly, and you know things can't travel faster than the speed of light, so you kind of have understanding of in time versus out of time.
Interesting.
And that's been a technology that's been developing kind of rapidly in the last 10 years. It's being implemented at the LHC. There's all kinds of, they use these things at the Atlas and CMS ideas for timing, for searching for long-lived particles and things like that. But that technology then can be adapted to a muon collider to kind of like use the caveman trick, the tracking trick, and the timing trick. And then it turns out that the actual signals that we'd see even at these highest energies are super manageable with full simulation studies.
Yeah.
The LHC is like such a crazy busy environment, and the computing capabilities aren't fast enough to keep up. What we do at the LHC is we actually throw away a lot of the data.
Yeah.
We have a so-called trigger that says, hey, if this isn't interesting, I'm just not even going to record it.
Yeah.
At the Muon collider, even at these high energies and with this beam and beam background, the idea is you could actually run the detector as a triggerless setup where you really could record everything. So it is crazier than electrons, but it's not as crazy as protons, and it looks like to be manageable with studies that we're doing now.
Yeah, amazing. There's this study by Lucchese. I can't remember the exact decay mode that it was, and it was only at like a few TV, but they seem to be saying no problem, we can do this, and if things keep continuing with machine learning, and as you say, introducing this timing information, it should be possible to do. So I'm getting those are sort of the technical details. I'm getting the sense, Patrick, is it fair as a summary of that kind of technical lowdown that, and I guess we've already kind of alluded to it, that everything looks like it can be done. It's just a case of getting some money, getting some interest, sitting down and putting this all in one place. Is that fair?
Yeah, I mean, there is a European study on this, and then the US study with snowmass. I mean, we really tried to look at all the different parts of it. And again, no one is saying this is going to come tomorrow. It really looks like it's probably on the order of 20 years. Okay, we need that kind of engineering commitment to it. But at the same time, there's no magic, no miracles that have to occur.
Yeah.
And it's just, if you make the investment, we can have this come. And hopefully we'll have enough foresight as human beings to say we're just as interested in probing the shortest distances as the biggest distances.
So that raises, as we kind of come to the end of this, there's no technical showstoppers, but as we kind of said, there can be money showstoppers, there can be interest showstoppers, there can be, conflict showstoppers. How would this machine fit in with the particle physics programs of a country that might host it? So, for example, the US or somewhere in Europe. How would you see this project getting off the ground and aligning well with some of their particle physics research programs so that it was taken up?
So I think it kind of really bifurcates into whether this happens at CERN or whether this happens in the US. So for CERN, definitely the emphasis is on the Future Circular Collider. And I think that if it turns out they can't get the funding to build this, that CERN would kind of go full steam ahead with the Muon Collider. I mean, obviously CERN is this wonderful laboratory that we've made in a different way than every other laboratory in some sense. And so from this perspective, I think it would just be, hey, if we can't do FCC, let's try to go to the Muon Collider, which is why the IMCC is hosted at CERN and funded by CERN. At the same time, we don't have to be in a situation where we only have one collider in the world necessarily. Okay, we've had many colliders operating at the same time. Other countries are interested in going in the high energy direction, like China, which will be interesting to see what they do. The US, though, it's kind of a very natural fit because the US used to have lots of colliders, but since the Tevatron closed down in the late 2000s, now we don't have a collider program. We switched to a neutrino program.
Yeah.
But secretly, that already was kind of the starting point for a muon collider, because as we said, we've made these muon beams before. We just then let the muons decay into neutrinos because that's what we were really interested in.
Yeah.
So the front end of a muon collider is just making all these muons. And that's really what we're focusing on in the US with LB and FDune. So it's obviously not exactly what you want for the Muon Collider, but it's kind of a step in that right direction. So I think there's two great options with CERN and with the US. And in principle, it doesn't have to be competing collaborations. Like the International Muon Collider Collaboration can kind of be the host, and then the site may end up being at Fermilab.
Yeah.
But it really is kind of a natural dovetail to the US, and which is why I think there's a lot of interest, not just as theorists who are all just happy with energy, but a lot of different parts of the US HEP community are interested in this.
I think they've got this nice diagram from your from the Muon Collider forum report, which basically shows exactly what you said, that these front end systems, which are the smashing into a target, creating the muons, which then decay to neutrinos, all these front end systems before you do the acceleration and the colliding in a ring, these are all the same for a neutrino factory creating lots of neutrinos, and for the Muon Collider. So you could imagine, I guess, it talks here about a neutrino factory, NUMAX, where you could have almost a kind of prototype facility that works on all of these front end systems and then uses them to create very, very intense neutrino beams. Why is a muon storage ring very, very good for neutrino beams? Is it because as they decay, you can create these collimated beams, or?
So the basic idea is like what you currently do with LB and Abdun or kind of any of these long baseline neutrino experiments are you have the muons that you're capturing to kind of make the beam, but they have a lot of spread of energy. So the neutrinos that you get out have a lot of spread of energy too.
Yeah.
And if you wanted to do more precision neutrino physics, you'd want to have a better characterization of the neutrinos that were coming out.
Yeah.
So you could kind of do this same front end. It turns out that the reason why these diagrams are slightly different is you don't need to do as much cooling to get a really nice beam, but you can kind of stop the cooling part at some point, like say I spend so much money to go to here, and then make this storage ring of muons, and then whenever you kind of have a straight section, well, all the muons will decay in the same direction, and then you'll get this collimated neutrino beam.
Yeah.
So it doesn't have to be the intermediate point. You could just do the Muon Collider, but it really does allow for this nice synergy between people that are interested in looking at the very highest energies and people that are really interested in looking at these most feebly interacting particles that we know of, neutrinos.
You said it doesn't have to be. You don't have to do it as a stopgap, but you can also think of it, I guess, as a spin-off benefit as well, right? Because there's one point about the Muon Collider which has always been a little bit of a or seen as a problem, which, as you said, these muons decay, they produce really, really collimated beams of neutrinos. Now, neutrinos aren't usually a problem, but then there's so many of these neutrinos that they can interact with the dirt and things nearby, potentially produce some radiation, which is dangerous. But if you can stop thinking of that as a problem, you can start thinking it as actually a production beam of neutrinos for maybe another experiment, which is kind of alongside the Muon Collider, right? So again, there's these kind of synergies that can happen.
Yeah, like in the case of the muon storage ring and all these neutrinos coming together, this is kind of a beam of low energy neutrinos. And it turns out the neutrino interaction cross-section with dirt or cement or whatever, it increases as a function of energy. So for a neutrino factory, kind of you never worry about these concerns whatsoever. If you go to super high energies, then you do have to start making sure that the radiation levels are tolerable everywhere. But like you said, it can kind of be a twofold step because yes, you want to make sure that there's no radiation that would ever affect the public in any way, shape, or form. That's obviously the zeroth order thing that you have to check no matter what. But you could also think of maybe for the first time ever, we could ask for what it looks like a high energy neutrino beam that you could do experiments there. I mean, we get high energy neutrinos at things like IceCube and whatnot, but we have no control over the initial conditions. Here, you could actually study these things in a different way that has never been done before.
Very, very interesting. That would really nicely fit in with that research program. So I've only got a couple more questions, Patrick. If you were going to build this thing, where do you think we should build it? Is it looking like Fermilab if that's the way we go because it's so well aligned with that physics program?
I think. I mean, again, this is the geopolitical, the money question. Sure. I think right now it makes the most sense for a future for Fermilab in the sense that there's a program of LB and Abdun that would naturally dovetail into the Muon Collider. The nice thing is CERN, of course, is this beautiful setup, which has a different sort of budgeting than the US budgeting.
Yeah.
So if CERN wanted to go ahead with this instead of FCC, I think CERN would be an excellent host lab.
Yeah.
I think from the perspective of though asking for R&D dollars in the US right now, the reason why it is a little bit attractive from that perspective is that it just fits so well programmatically.
Yeah.
So it is a natural extension.
Yeah, that makes sense. That was a good politician's answer as well. We'll have either. We don't mind. It was a very good answer. I liked it. So my final question, Patrick, is what are the steps forward on this? So I'm quite sold. I really like this idea, but FCC seems to be much more well advanced. Seem to have a kind of technical design report and more kind of technical details about how the collider might look. What are these steps forward for making sure that the Muon collider is seen as a potential alternate to that technology?
Well, I think you have to also view this about the energy scales, right? Because even if FCC goes forwards at CERN, the energy scales they're probing are very low energy. It's a Higgs factory that they're going after. And although it allows for a future proton-proton machine in the same tunnel, the time scales they talk about a 2070 start date, or I heard 2090 start date.
Yeah.
So, I mean, it really doesn't matter what the start date is when it's that far out in some sense. So from the perspective of muons, it's a technology that you could actually start probing these high energies on the time scale of 20 years from now. And I think the path to get there is to just start doing kind of some of the R&D to allow this path, because you want to have multiple choices in some sense of saying like how we choose these technologies to get there. And the nice thing is, because nobody's saying build a muon collider tomorrow, really there's the R&D that can be done now in terms of like the next 5-year period. It's still big in absolute dollars, let's say order 20 million, okay? But the actual HEP budget from the Department of Energy is 1.1 billion. So
for pocket change, get on with it. Give us some.
So this is just a matter of, I think, how we present ourselves to the public at large, in the sense of saying, like, if you make a smaller investment compared to all the other things you're doing now in the future, then we really can have a future that doesn't extend beyond all of our lifetimes, all of our children's lifetimes, all of our grandchildren's lifetimes. So I think that's the exciting thing about the field, that at least gives an option that with a sensible investment now, we really could probe these new energies that possibly could tell us about why is there a minus sign and we all exist and the Higgs potential within the next 20 years.
I was going to say, this is just from a selfish perspective, right? If we can get another, essentially a discovery machine in the next 20 years, rather than you were talking about things like 2090 to have another proton machine, I'm like, well, how old am I now? And no, I'm not going to be around for that. So just from a selfish perspective, and given the state of the field, it would be nice to have that discovery potential as soon as possible, right?
And it's not just purely from the physics. I mean, like I'll say, I'll have the selfish perspective too. I want the thing that gets there the fastest. But there's also kind of the continuity of knowledge in the entire field, where, I mean, sometimes theorists get kind of the most flashy perspectives in the public, and then experimentalists, you found a new particle, you get that. But there really is the bedrock that all this is built on are accelerator physicists, engineers. And building a collider, it's in some sense the most technically hard thing we know how to do in physics, in terms of all the moving pieces, everything to get together. And if there aren't new colliders going forwards, when you say the word 2090, none of the ones now are going to be around. And if there's never anything there, so it's a matter of, we need to make sure we make the investments as well, so that this knowledge isn't lost. Like, we don't go to a dark ages in some sense. Like, hey, we had this grand era of colliders, we forgot how to do it, and now we got to start again
You're
from
talking
scratch.
About the Artemis, it's like the Artemis program, right? Where we went to the moon and then we just sort of mothballed everything and then didn't bother going.
Exactly, and we don't want to have that situation, because there are other technological spin-offs of all these things that if we kind of invest in these directions, that it's not just like, I only care about the Higgs boson, so you should care about this. we're having a workshop in that INFN is sponsoring in Venice later in May. It's called Muons for the Future, where muons, obviously Muon Collider is the sexiest thing from my perspective, but we're using muons in new ways all the time. And because it's very hard to use them because they're not naturally occurring. We have to like get them, they decay quickly. But I mean, in the news, you've seen things like they've used it to image the pyramids of Giza because muons can pass through the pyramids. Cosmic rays can
I did
pass
a
through.
short on that one just today, actually. But yeah,
Exactly. I just saw some.
Yeah.
Yeah, they found that new chamber that they found it with the muons, and now they've actually found in person. And it's also useful for material science because you can kind of, just like we use electron rings and then use photons for synchrotron radiation, you can essentially kind of use muon beams to map out materials. And because like if you have a kind of a muon that gets captured inside of a material, then kind of the energy that the photons that come out, kind of like an NMR sort of situation, are higher energy. And so you can image high temperature superconductors that you can't do in other ways. So it really, it's not just for muon colliders, but muons really could be the particle of this century in new applications as well.
It's a total change in how we do things, and therefore the advantages that we'll get from that and the spin-offs that we'll get from that, we probably can't even, we can't even bookmark them all at the moment because we don't know what they'll all be. That's a very good place to end, and a very good message to end on, I think. Unless you have any other inspiring words on the Muon Collider, because I've got a little bit of a
we can always
section for
even
any
brand
other
it
business.
We could brand the 20th century as the century of the electron, and this century the century of the muon.
I like that. I think that's a very good way to leave it. So, Patrick, I'd like to thank you very much for taking the time today to go through that with me. It was absolutely fascinating, and I've really enjoyed learning more about this. I've done a little documentary style video on it, so I'll push people across to that as well. And Patrick, is there anywhere where you'd like people to go to learn more about this, learn more about the work you're doing, learn more about the Muon Collider? I know there's a sexy merch store now where I'm going to grab a t-shirt from. So there's lots of interesting things going on.
There's the merchandise store that we can link to for this, and then there's also a website that's being formed that has a lot of frequently asked questions and whatnot. It's muoncollider.us. It gives you kind of a feel of what are all the different aspects of this that are going on. And you can always find me on Twitter and ask any questions. And you can also, there's at Muon Collider on Twitter as well that other people are running that can answer all your Muon Collider questions.
Awesome. All of those links will be down in the description. So head over there and find out more about a Muon Collider. Patrick, thank you so much again for taking the time. I really appreciate it. Have a fantastic weekend, and hopefully we can chat again soon, buddy.
Thanks a lot.
Thanks.
Talk to you soon. Bye-bye.
Bye now. Bye.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.